In the light section, steel billets are precisely heated to optimal forging temperatures, enabling controlled hot forming into complex, smaller profile shapes with excellent dimensional accuracy and mechanical properties. Laser triangulation continuously scans profiles during production, ensuring precise shape, dimensions, and quality by detecting deviations in real time. These lightweight profiles serve diverse sectors, offering customized geometries and steels ideal for automotive parts, construction elements, and mechanical applications. Custom tools crafted for precise, efficient profile production. In the heavy section, large steel billets undergo thorough heating to achieve uniform temperature distribution. This enables robust hot forming processes that produce substantial, high-strength profiles. These profiles feature excellent straightness, tight tolerances, and mechanical properties essential for demanding applications like industrial trucks, cranes, and heavy construction machinery. These robust profiles support heavy-duty applications, delivering strength and durability for industrial trucks, commercial vehicles, construction equipment, and structural engineering projects. Powerful water jets remove surface scale from hot steel profiles in a fully automated process, ensuring clean surfaces, improved quality, and optimal conditions for subsequent processing and inspections. Ensures precise dimensions and flawless surface quality. Automated robots efficiently arrange steel profiles into customer-specific stacking patterns, handling lengths up to 24 meters, enhancing safety, optimizing space, and ensuring reliable, damage-free product handling. Laser sensors ensure precise shape and alignment. The advanced stacking system organizes steel profiles into customized bundles based on fixed lengths, accommodating diverse customer specifications. It ensures optimal stability, efficient space utilization, and secure transport. Precision handling minimizes product damage, streamlines logistics, and supports flexible delivery requirements for various industries, enhancing overall production efficiency and customer satisfaction. A bulbous panel, often used in shipbuilding or architectural applications, features a curved or bulged geometry that enhances strength, aesthetics, or hydrodynamic properties. Producing such panels demands precision forming equipment, like the Nieland press, known for its efficiency in shaping complex, large-scale metal components. The Nieland press operates using a cold forming process where a steel plate is incrementally pressed into shape by hydraulically controlled rollers or dies. The production begins with selecting an appropriate steel plate, typically mild or high tensile steel, depending on the application's strength requirements. The plate is measured and positioned accurately on the press bed. The unique feature of the Nieland press lies in its programmable control system, which allows operators to input the precise curvature profile of the bulbous panel. As the press cycles, rollers or forming tools apply pressure progressively across the plate. The combination of controlled force and strategic positioning prevents material thinning or excessive stress, ensuring uniform curvature. Throughout the process, technicians perform frequent inspections, checking the panel's curvature against templates or digital measurements. Advanced Nieland presses may include laser scanning systems for real-time geometry verification, further improving accuracy and reducing scrap rates. After forming, the bulbous panel may undergo additional processes such as trimming, edge preparation, or welding stiffeners, depending on design requirements. Surface treatment or shot blasting may follow to prepare the panel for painting or coating, especially for marine applications where corrosion resistance is crucial. Explosion bond clad pressure vessel fabrication is a specialized manufacturing process used to create vessels capable of withstanding high pressures and corrosive environments. Explosion bonding, also known as explosive welding, joins two dissimilar metals, typically a corrosion-resistant alloy, like stainless steel, titanium, or nickel alloys, and a lower-cost base metal such as carbon steel. The process uses controlled explosive energy to drive the clad material onto the base metal at high velocity, forming a metallurgical bond without melting either metal. The resulting clad plates combine the mechanical strength and cost-effectiveness of the base material with the corrosion resistance of the cladding layer. These clad plates are then shaped and welded into pressure vessel components following stringent codes like ASME Section 8. Fabrication involves forming, cutting, and welding processes while ensuring the clad layer remains intact and free from defects such as delamination. Explosion-bonded clad vessels are widely used in industries like oil and gas, chemical processing, and power generation, where both structural integrity and corrosion resistance are critical. This technique offers significant cost savings compared to solid alloy vessels, while maintaining excellent performance and extending service life in harsh environments. The flange manufacturing process begins with heating a steel billet until it becomes malleable. The hot billet is forged into a rough flange shape using a hydraulic press. Next, CNC machines precisely expand and shape the inner diameter to meet specific size requirements. Depending on the flange design, further forming and machining refine the dimensions and surface finish. After forging and machining, the flange cools gradually in controlled conditions to relieve internal stresses and enhance material strength. Finally, rigorous quality checks using advanced measuring equipment ensure dimensional accuracy, surface quality, and structural integrity. Only flanges meeting strict standards are approved for use in piping systems, ensuring reliability and safety in various industrial applications. Stainless steel is a remarkable material known for its shiny appearance and resistance to rust and corrosion, qualities it retains even when made from recycled materials. The journey to produce stainless steel begins with collecting scrap metal, such as old sinks, kitchenware, and industrial equipment. These metal scraps are melted together in a powerful electric furnace, where intense heat is generated by electric arcs, sometimes producing dazzling sparks reminiscent of fireworks. During melting, specific elements like nickel and chromium are added to the mixture. Nickel enhances the steel's strength and toughness, while chromium is crucial for protecting the steel against corrosion. These alloying elements transform the molten mixture into stainless steel with the desired properties. After melting, the steel undergoes a refining process to remove impurities. Metallurgists blow argon and oxygen gases through the molten metal, causing unwanted elements to bind together and form slag. This slag floats to the surface and is removed, leaving behind a purer, high-quality molten steel. Throughout this stage, precise control of temperature and chemical reactions is essential to ensure the correct composition and quality of the steel. Once refined, the molten stainless steel is poured into molds to create large solid shapes called slabs or billets. These semi-finished forms are then reheated to make them softer and more workable. The hot steel passes through massive water-cooled rollers in a process called hot rolling, which stretches and thins the steel into long strips that can sometimes reach lengths of up to 600 meters. These hot-rolled strips are subsequently cooled and coiled for further processing. The next step involves cleaning the steel to remove surface impurities, such as rust and oxide scale. This is achieved using hot acid in a procedure called pickling. The steel is then annealed, meaning it is heated and cooled slowly to relieve internal stresses and improve its ductility. This process further refines the steel's finish, making it smooth and shiny. An essential characteristic of stainless steel is the formation of a thin chromium oxide layer on its surface, which occurs naturally and acts as a protective shield against rust and corrosion. Finally, The stainless steel sheets are cut to size and prepared for use in countless applications, from kitchen appliances and medical instruments to construction materials and automotive components. Through careful processing and advanced metallurgical techniques, stainless steel emerges as a versatile and durable material used around the world. The manufacturing process of a bronze bushing begins by heating bronze to around 600 degrees Celsius, making it soft and workable. Once malleable, the bronze is carefully shaped to precise dimensions using specialized tools and machinery. Precision is vital, especially when drilling holes or refining measurements to ensure the bushing fits exactly as required. Skilled workers handle the hot metal safely and constantly check measurements to prevent errors. Throughout production, the bronze bushing is inspected for weight, size, and overall quality to meet industry standards. After shaping and drilling, the part is cooled under controlled conditions to maintain its structural integrity. Finally, the cooled bushing undergoes finishing processes, such as smoothing or polishing, to achieve the desired surface quality and performance characteristics. Experienced operators oversee every step, ensuring that the finished bronze bushing is durable, reliable, and ready for use in mechanical systems. The Sumitomo 6,500-ton hot forging press is an advanced manufacturing system engineered to produce large, high-precision crankshafts for demanding applications like marine propulsion systems, locomotive engines, and power generation machinery. With a formidable capacity of 6,500 tons of force, this mechanical press can shape sizable steel billets at high temperatures, ensuring both accuracy and repeatability in forging operations. The process starts by heating the billets to around 1,200 to 1,250 degrees Celsius, allowing the steel to flow and fill complex die cavities effectively. Equipped with automated billet handling, precise die alignment, and sophisticated process monitoring, the Sumitomo press supports multi-stage forging operations, such as preforming, blocking, and final forging. These stages are critical for optimizing grain flow and refining the internal structure of the forged parts, directly contributing to the crankshaft's strength and fatigue resistance. Its closed die forging configuration ensures tight dimensional tolerances and uniform structural integrity across each part. Following the forging process, operations like flash trimming, controlled heat treatment, and rigorous ultrasonic inspection are integrated into the production line. These post-forging steps are vital for removing excess material, achieving desired mechanical properties, and verifying internal quality. At Aceros de Guatemala, the manufacturing of steel rebar begins with scrap metal, which serves as the primary raw material. This scrap is first prepared through a process known as industrialization, aimed at increasing its density, removing impurities, and reducing contaminants. Once processed, the scrap is loaded into baskets using a 15-ton crane. Each basket holds up to 25 tons, and the total load reaches about 60 tons before being charged into the steelmaking furnace. The scrap is melted at temperatures around 1,600 degrees Celsius to produce molten steel. The molten steel is then transferred to the continuous casting machine. This machine comprises a rotating turret that receives the ladle of molten steel. The steel flows through a distributor into 4 copper molds that shape it into billets, or palanquillas, typically 12 meters long. These billets are the primary input for the rolling mill where rebar is produced. Billets can be transported hot directly to the rolling mill or stored and later reheated. In the rolling mill, billets enter a reheating furnace that raises their temperature to approximately 1,150 degrees Celsius over a period of about 3.5 hours. 2 hydraulic cylinders push each billet into the furnace, which has a capacity for 118 billets and operates using bunker fuel and air. After exiting the furnace, the hot billets travel on roller conveyors to the first stage of hot forming, known as roughing. During this stage, significant reductions, up to 25% per pass, are achieved across 7 rolling passes. The billets pass through specialized rotating rolls that progressively reduce their thickness and shape the steel closer to its final dimensions. In subsequent forming stages, rebar is further shaped and, depending on size, can be produced using a method called tri-slitting, which allows up to 3 rebars to be manufactured simultaneously. Rebars of up to 72 meters are cooled on a cooling bed and then cut into standard lengths of 6, 9, 12, or 15 meters. A hot forging press line rated at 12,500 tons is a powerful industrial system designed to shape heated metal billets into precise components under immense pressure. Operating at temperatures typically above 1,000 degrees Celsius, this press line can handle large and high-strength materials such as steel alloys, titanium, or aluminum. Its enormous tonnage allows the production of sizable parts with complex geometries, essential in industries like automotive, aerospace, and heavy machinery. The line often includes automated handling systems, induction heaters, and sophisticated dies to ensure high productivity and repeatable quality. Advanced controls monitor temperature, force, and stroke to optimize the forging process and minimize material waste. Components forged on such a press line exhibit superior mechanical properties, including enhanced strength and fatigue resistance. Free forging, also known as open die forging, is an essential technique for producing custom components like special pistons that demand high strength, durability, and precision. In the manufacturing of such a piston, a power hammer plays a pivotal role, delivering controlled, high-impact blows to shape the hot metal into the desired form. The process begins by selecting a suitable material, often a high alloy steel chosen for its strength and resistance to heat and wear. The steel billet is heated in a forge to temperatures ranging between 1,100 degrees Celsius and 1,250 degrees Celsius, where it becomes malleable yet retains sufficient cohesion to prevent cracking or tearing. Once heated, the glowing billet is transferred to the anvil of the power hammer. Here, the blacksmith, or skilled operator, maneuvers the metal, while the power hammer's ram descends repeatedly, delivering precise, rhythmic blows. The operator rotates and repositions the workpiece to distribute the deformation evenly, gradually reducing the billet's thickness and elongating or widening it as needed. This step is crucial for achieving a homogeneous grain structure, enhancing the piston's mechanical properties and fatigue resistance. During free forging, the piston's basic shape is roughed out. Unlike die forging, where closed dies impart the final shape, free forging relies on the operator's skill to sculpt the material. The power hammer allows for quick material movement and excellent control, enabling the smith to create features like the piston skirt, boss sections, or thickened areas intended for pin bores. Once the piston blank reaches approximate dimensions, finer adjustments are made using lighter blows or different dies fitted to the power hammer, such as fuller or flatter dies. Periodic reheating may be necessary to keep the metal workable. Throughout the process, frequent measurements ensure the part remains within the required tolerances. After forging, the piston is cooled gradually to relieve stresses. The rough forged blank then undergoes machining processes like turning, milling, and drilling to achieve precise dimensions, smooth surfaces, and any required internal features. Heat treatment may also follow to optimize hardness and toughness. The Clinton bar mill supplies hot-rolled bars with sound center integrity, ranging from 6 inches to 16 inches in diameter and up to 40 feet in length. Larger bars are produced using open die presses. Each tartan bar undergoes a preliminary forging stage to consolidate the core, followed by repeated planishing passes through rollers to achieve a consistent rolled surface. This process ensures a minimum center reduction ratio of 3:1. Bars can also be peeled or machined to meet customer specifications. Optimized roll sizes reduce excess stock, while efficient production scheduling ensures consistently short lead times.